let us start this lecture with a statement from great scientist Albert Einstein, who happens to be my favorite scientist. He says that everything should be made as simple as possible, not simpler. Think about it. You need to think about it. Maybe we will discuss later on, but let us recall what we did in the last lecture. Can anybody tell me what did you learn? Because recalling is a very important aspect of learning. You need not look at notes, rather recall from your mind. Let me tell that what we did, we started the class with the concept of using the various coordinate system, whether flow will be one dimensional or two dimensional or three dimensional, and when we are talking about it, which coordinate system we should use, whether it will be rectilinear coordinate system or cylindrical coordinate system or the spherical. And it is important to know the which one you should use where, but in most of the aerospace application, particularly propulsive devices, we prefer to use cylindrical coordinate system, because it is easier to analyze and write the equations. And then we move into how to derive the governing equations to carry out quantitative analysis. And the governing equations are based on the principle of conservation of mass, energy and momentum. And of course, we have not discussed about conservation of what you call the species. It is not species, rather the mass being conserved. The species equation we did not discuss, but however, we will be discussing it whenever we will be venturing into analyzing reacting flow in case of combustion. And we also added one equation, that is equation of state, particularly for an ideal gas. In other words, it is the ideal gas law which we have included in the governing equations. And all these equations, if you look at it, quite complex, right, and those equations has been derived since a long time. But if you look at particularly Navier-Stokes equations, is not being solved in totality. That is the big challenge, right, yet to be resolved. You can solve the Navier-Stokes equation, or you can solve it by computational method, which is an ad hoc solution rather, but there is no identical solution for the Navier-Stokes equation, complete Navier-Stokes equation till now, but some simpler one you can get, like Poiseuille flow, boundary layer flow, Blasius equations and other thing you can solve. That means, if I look at really this mathematics is not growing at this moment, it has stopped growing since a long time back. And some of you could solve, then it will be a great thing as such. So, therefore, another scientist who is Richard Feynman, who is a very great person, he says that we have written an equation does not remove from the flow of fluids its charm or the mystery or its surprises. If you look at the way he has stated this, this sentence, he says what is the feeling for the fluid mechanics he was having, and he is one of the greatest scientists in last century, right. And if some of you might have read his book, surely you were joking, Mr. Feynman. Any of you have read? Right? It is a very wonderful book. He has written another book also, You Are Okay, I Am Okay, by Richard Feynman. And he is having a series of books, the volume 1, volume 2, volume 3 on lecture notes on physics, which some of you might have. If not, then look at it. It is a wonderful book. So, and components also is there on fluid mechanics. So, now we will be trying to look at the basic principles of compressible flow. In some books you will find it is known as gas dynamics. How it is different from the aerodynamics? Can anybody tell me, or it is the same? Of course, one can say that flow related to the air, you can call it as a aerodynamics, but then how the gas dynamic is different than that? Aerodynamic is the whole gamut of the fluid mechanics or fluid dynamics related to the air. But however, in case of gas dynamics, we will be confining to the compressible flow. That means, question arises, what is a compressible flow or what is an incompressible flow? That means, if compressible flow is there, there is another flow which is incompressible, right. When you talk about it, then naturally question arises that what is it, flow will be incompressible or flow will be compressible, or fluid will be compressible or fluid will be incompressible, right. So, what is the meaning of it? How we will judge whether it is compressible or incompressible? If I take a solid one, let us say if I take a chalk, right. Of course, if I apply a very little pressure, what will happen? There is no change in its shape or size, right. But if I apply a large amount of pressure, then what will happen? It will break maybe, right. But if I take a what do you call a water, right, and I am trying to pressure it. For example, if I take in a syringe, right, and I have taken water here, right, and syringe, what I am doing? I am just trying to press it, right. Is it possible I can press it? I cannot. Why? Because if I am pressing it, is it any change in the volume? There won't be change in the volume, but if I take air, right, if I take air, right, and try to, let us say it is here, I am trying to press it, I am close, keep in mind that I have closed this inlet or the nozzle and I am pressing it, I could press it. Of course, after a certain time it is difficult, I need to pressure more, put more force or the pressure, right. That means, what it says? It says that the air is compressible and water is incompressible, right. That means, the change in the pressure, or change in the force what is being applied, it will be changing, change in the pressure, or when I am applying pressure, its volume is changing, right. And if volume is changing, then I am calling it as a compressible. If it is not changing, it is an incompressible, right. We will take a maybe a fluid element just to illustrate it further, and this pressure is applied on this fluid block, which is having, let us say, one unit block. That means 1 centimeter, 1 centimeter, 1 centimeter cube, and is having certain volume, right, and I am applying the pressure, let us say P all are there, it is in equilibrium, right. If I go on adding this pressure, let us say dP here everywhere, right, all the places, then what will happen? That means, it will be subjected to strain, provided it is a fluid, right, it is compressible, right. For example, if I will do, then what will happen? This volume has been changed due to the application of pressure which was in equilibrium, if I consider as a fluid element, right. Now, what is happening? The change in the volume is happening with the pressure. So, then if I want to judge quantitatively, because this I am talking about qualitatively, it is being decreased, but if I want to quantify it, then I need to define a term, right, which I can call it as a compressibility, which will indicate how far it is compressible right. Then what I need to do? Basically, it is the same thing. What I have to do? Change in specific volume per change in the pressure per unit specific volume. We call it as a compressibility, right. K, and where this minus sign comes from where? Because always whenever you are applying some pressure or the force, there will be change in volume. It will be decrease in volume. This decrease we call because of this, because in the final volume minus the initial volume divided by the pressure change over the unit specific volume, therefore, negative sign comes into picture. Now, whenever we are saying this, is it good enough to say this? Because we know if I take a cycle pump, maybe earlier days, I remember when I was a kid, we used to pressurize or inflate the tube of the cycle or the by using a piston cylinder pump or air pump, piston cylinder air pump, right. This will be like you will have to do this. Then if I apply the pressure and go on inflating my tube, then what I will feel? What is happening to the cylinder if it is metallic? Okay. Nowadays, of course, people are not using metal, so you will not feel it whether it is hot or cold. What it will be? It will be hot, right. Why it will be hot? Huh? There will be two reasons. One is that because the pressure you are applying, this molecules will be compressed, then there will be increase in pressure in the cylinder and there will be temperature. Beside this, like piston is moving, so there will be rubbing action, friction will be there. So, there will be heating some being generated also, but those things we will be saying it is neglected as compared to that for the sake of discussion. However, you cannot neglect it. So, naturally this compressibility what we talk about is not really good enough, right. That means, I need to define a term which will be either that means temperature should be remaining constant. That if I do it, I call it basically isothermal compressibility, right. And how I will define it then? This will be minus 1 over nu and dou V by dou P T, right. And keep in mind that this is a what you call the partial derivative. And similarly, if there is no heat loss, if I take that example of piston cylinder, then I can define another compressibility, right, because there is no heat loss. So, it will be adiabatic. If I assume it is isentropic, that means there is no effect of friction in that, right, isentropic, reversible, right, then I can call it as another what you call compressibility is known as 1 over mu d by dP. I am saying Is, isentropic, right. And we know that specific volume can be related to density, because V specific volume is 1 over density. So, if I write down this equation compressibility, I can write down K is equal to 1 over rho d rho by dP, and that is basically compressibility. Similarly, you can talk about isothermal compressibility and isentropic compressibility by the partial derivative, keeping one of them constant, right. Now, if I talk about this compressibility, right, is it I am talking about fluid or I am talking about flow? So far this compressibility is concerned. It can be fluid, it can be flow as well, right. We will see later on. Let us consider this as a fluid. For example, if I take this compressibility K value for a water, what it would be? 5 into 10 power to minus 10 meter square per Newton, right, at 0.1 megapascal and 298 Kelvin, okay, because that will be dependent on that. And whereas for air it will be 5 into 10 power minus 5 meter square per Newton at 0.1 megapascal, T is equal to 298 Kelvin, right. So, if you look at the what is the difference, if you take a ratio, what it would be? It will be 4 order of magnitude between the water and air, right, compressibility. Higher the compressibility, right, higher this compressibility factor, what it will be? Then more it will be compressible, right. Am I right or wrong? Higher compressibility. So, therefore, like water is considered as to be incompressible fluid. But if I apply very high pressure, let us say 1000 bar or more than 1000 bar, can I call water as a compressible substance? Certainly no, because the pressure is quite high, right. But if I am applying, let us say maybe 10 bar or 5 bar, I can assume it to be water as an incompressible fluid. 1000 bar is a very big amount of pressure, right, or maybe 2000 bar is quite big. So, therefore, in practical sense the water is considered to be an incompressible fluid. Now, let us see that whether we can apply this for a flow. That means, if flow is taking place, right, and you are having a stationary and you will pass through a nozzle, right. Suppose this is a very infinite reservoir, and this is your nozzle where flow is taking place. This is the reservoir. At certain pressure of what you call T and P, right. Here velocity will be 0 and some pressure will be there, P. Atmospheric pressure, keep in mind that this P is much higher than atmospheric pressure. So, you will find there is a velocity, finite velocity, maybe let us say 20 meter per second, or maybe it can be 20 meter per second, right, let us say. Now, this why it is occurring the flow? Because there is a pressure gradient, right, because when fluid is flowing, why it is flowing? Pressure gradient. We know that temperature also flows because of temperature gradient, but why it is really flowing, do you know? If you go back to the concept of equilibrium, it wants to attain the equilibrium, therefore, it is flowing. Similarly, we do some kind of work, right. It is basically the all activities is because of gradient, any activities which is occurring, but ultimate objective of thing is that you need to attain equilibrium. That is the beauty of all the natural processes, and so also the human life, we should attain equilibrium, means peace and bliss. So, coming back to this, that if fluid is flowing because of pressure gradient, then there will be change in density, right. If I rewrite this equation 1, then what I will get? I will get that d rho by rho k dp, right. What is saying? The change in density will be occurring, which will be proportional to the change in pressure, and also it will be proportional to the compressibility. Sometimes you call compressibility factor, right. So, if you look at, if it is a what you call a higher value, right, for example, 5 into 10 power minus 5 meter square per Newton for air, then naturally change in the density will be higher for the same pressure change, if I consider water and air, right. And if this pressure will be higher, then what happens for the same air? For example, instead of 20 meter, if I say it is something 300 meter per second, right, or 200 meter per second, this velocity, because I need to have a much higher pressure between this nozzle, right. Then naturally my change in density will be higher, where I cannot neglect, but if it is 20 meter per second this velocity and correspondingly the pressure gradient which is occurring across the nozzle, then naturally I can neglect it, the change in density, because the pressure gradient across the nozzle is small. So, therefore, that we can say that the flow will be incompressible almost if the pressure gradient across a flow is very, very small, leading to the change in velocity will be also small, right. That means, this compressibility can be related to not only the pressure for the to the velocity as well. Now, how we will judge it, whether it will be compressible or incompressible? For that, we need to look at certain better quantities. Okay. For the practical purposes, what we do, that we say compressible flow wherever the change in density is greater than equal to 5%, then we call it compressible flow. If it is incompressible flow, then the change in density must be less than 5%, right. And this is a little roughly we are talking about from practical point of view, but however, we will again revisit it. But let us understand how we can really say whether the flow is compressible or not. As I told, that means velocity is the one quantity we can talk about, because I told the velocity when it is 20 meter per second, we can call it as consider it as an incompressible flow, although it is air flow is, we are considering the air flow, and whether it will be really compressible or not, or it is just a assumption, that we will see little later on. But as I told you that it is related to the velocity, and when you talk about velocity, we need to also define also look at a sound. That means, speed of the sound we need to understand. But let us first ask a question, what do you mean by a sound? Can anybody tell me? For example, I am talking, right? You could hear it, that means I am producing some sound, yes or no, right. For example, you are around maybe 2-3 meters away from me sitting, and you could hear if I am speaking in a audible voice, normal audible voice, right. But if you are sitting, let us say 200 meter away from me, can you hear this sound? You cannot really. If you are in between maybe 50 meters or a 20 meters, you may feebly hear, try to right. So, then what do you mean by sound? How it is? What is the mechanism of this sound? Because if I am generating a sound here, you could hear from a distance. So, naturally it is moving, right, it is propagating. If it is propagating, right, how it will be propagating, what is the mechanism, how we can quantify it, whether it will be dependent on the medium or not. For example, instead of now it is the air between, let us say I am in water, like in a swimming or in a sea deep, like swimming nowadays, deep water swimming people are enjoying today, with the modern technology, right. So, that whether you want to make a sound, whether you could hear or not, or if I go to the vacuum in the space and I will be talking, whether you could hear or not, right. So, these questions we need to understand a bit, and for that for example, we know that the speed of sound will be less than the speed of light. How do you know that? Do you have an experience? Yes, certainly yes. If you observe, nowadays like your rainy season where thunderbolt is likely to occur and you see the lightning, but after a long time or maybe certain time you could hear the thundering sound, but already the spark has occurred. So, therefore, you could see that the speed of sound will be lower than the speed of light. But however, what is the mechanism of sound? I will take an example of firecracker, right. If a firecracker will be off or it will be busted out, then what happens? There you produce a detonation. How do you produce the detonation? You basically initiate the combustion reaction. That means, some amount of chemical energy is converted into a pressure energy or so that it will be released and adjacent molecule will be get affected by this, right. The molecules will be moving at a higher velocity, although all the time molecules will be in random in nature moving, but this will be colliding with the other molecules, right. And then it will be as it is colliding adjacent molecules, it will be propagating, right. And then you could hear in your eardrum will be vibrating, and then you could hear the sound, right. If you look at what is really happening whenever this molecular interaction takes place or molecular motion takes place, what really happens? There will be change in pressure. If there is a change in pressure, there will be change in density, because we are talking about in air medium or the gas kind of thing, there will be change in temperature as well, right. If there is a change in pressure, change in temperature, we have seen that means it will be moved like and creating a molecular motion, right. And can we call it as a wave? Because some people say sound wave kind of things, right. And wave, what kind of wave? Whether it will be a longitudinal wave or a transverse wave, right. What it would be? The transverse wave. Let me understand what do you mean by transverse. Suppose I will put a stone in the still water, right. What happens? There will be ripples. Have you observed that when you were a kid particularly? Like there is a here and then ripples will be there, right. If I take these things, let us say there is some sound generated at the center, then it will be moving. If you look at these particles are being compressed over here and expanded and compressed, and it goes on. So, it will be moving in this direction, right. So, therefore, this is known as a because with the length along with the radial direction it is moving. In gas medium or the liquid medium, it will be moving in a what you call longitudinal. But whereas, in the case of solid through which sound can also move, it can move both the longitudinal and the transverse direction or transverse waves, right. So, therefore, sound whenever you say it is a both combination of it, but it moves in the longitudinal. If you want to see this how it is to have a feel it, you can go to the Wikipedia and then you see this animation. I have taken this picture from that. So, therefore, we can define what you call a sound wave is a weak compression wave across which infinitesimal change in fluid properties occurs, right. When it is occurring, the fluid properties change, right. Then we call it as it will be moving with certain velocities, and we will be interested in speed of sound, right. And as I told you, while discussing about mechanism of sound, that molecules will be colliding and moving. That means, there will be whenever average molecular velocity whenever there is a sound being impose on it, right. Okay. Now, if you look at, that means there will be increase in average velocities of the molecule. So, if I can invoke the molecular theory of gas, right, or kinetic theory of gas, I can get the velocity, I can relate this speed of sound to the average molecular velocity. If you look at, some of you might have studied that in your +2 or maybe in engineering, we know that this what you call the molecular velocity, average molecular velocity V will be equal to 8 R T by pi root over. This is the molecular velocity, okay. Average molecular velocity. That means, you will say that it will be dependent on temperature, and you can roughly get that the speed of sound is basically 3/4 of this molecular velocity. You can look at it kind of from the kinetic theory of gases, but however, we will not be resorting to that. We will be not interested to look at microscopic effect, rather macroscopic effects kind of things, right. Now, one idea is crossing my mind, I want to cross check, whenever this pressure or the wave is concerning, there is a change in the pressure, right. What would be the change in pressure? What will be the order of magnitude, right. We will get to that. Let us understand that there is a is a piston cylinder arrangement I have taken, where you are just pushing this pressure with the piston with certain force. What is happening? It will be creating some kind of a change in velocity, right. When it is changing, the adjacent molecules will be having a certain pressure P plus dP, whereas away from that, at the stationary, where the fluid will be stationary, it will be P and density rho and enthalpy H, whereas here there is a change because of piston is there. You are creating a small disturbances, right. And as a result, there is a wave which will be moving, because it will be compression, the way it is moving in this direction. So, what is that? With what it will be moving? It will be moving with the velocity a, right. Let us say this is a wave which is moving with certain velocity, we are calling a. A is basically we are calling speed of sound, because these disturbances is creating the sound. Okay. Now, coming back to the what will be there will be change in the velocity, and here we are saying it is a certain velocity, there is a change. Of course, this is a 0 here, right, it has come to 0 velocity stationary to start with, and similarly there will be change jump in pressure, and keep in mind this is the model, but actual system will be like this in reality, but here we are calling it as a step function. Okay. You please keep that in mind, which will be moving at certain velocity of a, right. This will be moving. Now, if I want to make it stationary, what I will have to do? You will have to sit in this wave which is propagating this in the x direction, then what will happen? You feel as if the fluid is coming from this side and you are stationary, right. This concept is very important, right. Then we will get as if the fluid is coming from this side and with a certain velocity of a, and there is a change in velocity because dV is coming opposite to that. So, then the pressure P rho and dH, and it is getting compressed P plus dP, rho plus d rho and H plus dH. If you look at it is a 1 and this is the 2, right. Okay. Is that clear? This is a very important concept which you should keep in mind. But let me try to answer that question what I told you, that what will be the pressure whenever suppose I am making a sound, right. There is atmosphere, silence, nothing is there. What will be the pressure? Atmospheric pressure, right. That is 101,325 pascals, but that depends upon height, as I told you, depends upon temperature, depends several things, but atmospheric pressure will be there. We can roughly say it is 1 bar, right. But if I make a noise or a sound, what will be the change in pressure? It will decrease? Certainly no, it will be increasing, right, or it can also decrease. It is not that it will not decrease only, it can increase and decrease, right. What it would be? If I plot this pressure versus time, whenever the sound is created, what it will be? It will be something like that, depending upon, it need not to be so regular I have drawn, okay. But if I say this is the pressure which is average pressure, this is my ambient pressure, this is ambient pressure. And there will be our change in the pressure, peak values, and there is a decrease in pressure. What I will zone this will call? This will be silence, right. There is no change in pressure, right. But however, there will be, this zone is noise. But what will be change in this pressure, that is my question. Okay. Of course, it will be having amplitude, what I have shown here, and is having certain frequencies, right. We know that we can hear human being from 20 hertz to 20,000 kilo or 20 kilohertz, but actually it is 18 kilohertz, but we just to remember we say that, okay. Right. There is a frequency, but what will be that value? I want to hear from you. Will it be, that this pressure will be what? It will be approximately Pascal, right, 10 power to 5 Pascal, right, yes or no. Now, what it would be? What is the change why you will get? Suppose I am speaking, now there is a jet noise, jet in the sense aircraft is moving, jet engine is moving, what will be noise, right? It will be how I will express this sound in reality. You might be knowing decibel we use, right. The change in pressure will be what order? For audible, it will be generally 40 to 60 decibel, right, audible, whatever the way we talk, okay. Unless you are shouting, it will be little more, okay, or there is a melodious voice, it will be little, depending upon, by mine will be maybe 50 kind of decibel, right. But what will be the pressure then, amplitude? Will it be 1000 Pascal, will it be 10,000 Pascal, or will it be 5 Pascal, or what will be, what I am giving you, see, you have all studied sound a lot, physics you have completed. I am asking very simple question. I am giving what will be the sound, I am talking now, what will be order, I am not saying exactly you tell me. Certainly no, you will be surprised, it will be very, very low, it is in micropascals, okay. So small thing is making that change, and of course, it can be a very higher range, but it can never go to the 1000 or Pascal, okay, you will go deep, right, okay. So, therefore, you should have a feel for it, it is very important, okay. Writing equation is okay, you can derive, but those things. Let us look at now, get into that what we will be doing is what we are taking this moving, and we are taking this control volume CV, and which will be considering inlet and station 1 and station 2. What we will be doing now? We will be applying the equations what we have already discussed, that is continuity and then momentum, then an energy, all those things we will be looking at it. And what we will be doing now? We will be looking at mass conservation, that is what? It is a one dimensional flow, keep in mind that is the steady, right. And then what will be then mass conservation equation, that is m dot 1 is equal to m dot 2, there is no accumulation because it is a steady process. So, I can write down m dot 1 is equal to m dot 2. So, then if I write down here what is the density? Density is rho here and A, and this area cross section area I am taking as A. Okay, that is the cross sectional area. That means, this is the mass flow rate into rho plus d rho into A minus d v, the velocity, into area. I can cancel this out, okay, and then expand it. If I will do that, what I will get? I will get in the left hand side rho A is the, keep in mind, small a is the speed of sound, A is the cross sectional area. You can cancel, it could have been more simpler, maybe I can cancel right now here. So, nothing to worry about much, okay. And then what I will get? Rho A, and this will be rho A minus rho d v and d rho A minus d rho d v. And if you look at these terms will be higher order terms, because this change in the pressure, I have told you what will be the atmospheric pressure, let us say, and this pressure change is very small. Therefore, I am saying it is infinitesimally change, okay. It is really neglected, but it is having effect. So, if it is order, then I can neglect this term, right. And similarly, so what are terms remain? That is rho d v is equal to A d rho. So, I can write down the A d rho, this term minus rho d v is equal to 0, that is equation 3. Okay. To where 3 comes, okay, fine, all right. So, the energy equation I can look at the same way, h plus s square divided by 2 is equal to h plus d h plus A minus d v whole square divided by 2. What are the assumptions? It is basically adiabatic process we are assuming, and then steady flow, right. These are the assumptions we are making. Now, if I just I can cancel here and expand it, and higher order terms I can neglect, then I will get d h minus d A d v is equal to 0, that is the equation number 4. Now, we will considering the propagation of sound wave to be isentropic. That means, not only the adiabatic, but there is no change in entropy across the thing. Then we can have the T d s is equal to d h minus v d p. You know this equation, this is known as Gibbs first equation. Is a combination of first law of thermodynamics and second law of thermodynamics. If it is isentropic flow, so then I can say this is 0. So, then this equation could have been d h is equal to v d p, and keep in mind that I can write down instead of v 1 over rho. So, I can write down d p by rho. Now, what we will do? We will combine this mass conservation, energy conservation and this expression and look at what we are getting. So, what we can do? We can start with this equation 3, A d rho minus rho d v is equal to 0, and then A is equal to rho d v by rho. Can I write down this way? Is equal to, right, instead of d v, right, this d v, if you look at, I know from this equation 4, what is this d v? d v is equal to d h by A. But what is this d h? d h is basically d p by rho. So, I can write down d p by rho and A, right, and in place of d v I am writing rho d p A and rho. So, I can cancel this rho, right. Can I not cancel? Then what will happen? Then this will be A square is equal to, I can write down d p by d rho, that is A square is equal to d p by d rho. Okay. So, that means what is saying the speed of sound, square of speed of sound is basically change in pressure with respect to change in density, or it is other way around, 1 over change in density with respect to change in pressure, which is very simple, and it is valid only for an isentropic flow. If it is isothermal flow, this equation will be valid or not? It will not be. Do not say yes, it will not be, it will be changing, right. And A is the speed of sound, as I told. By using this isentropic relationship, like that we know P v gamma to the constant for an ideal gas, that is P v power to the gamma is equal to constant. And what we will do now? We will try to differentiate this and put into this equation. That is, of course, we can write down P is equal to C rho gamma, because V is equal to 1 over rho, right. So, I can write down P is equal to constant into rho gamma, then I can put this equation, I can differentiate it and I can simplify that thing and then write down dP by d rho is equal to gamma P by rho, and if I use ideal gas law, that is P is equal to rho R T, then I can write down P in P divided by rho is equal to gamma R T. So, if you look at this, we can now speed of sound square is related to gamma R T, right. You remember that I told you the average molecular velocity is basically also in similar in nature, right. So, now if I take the root of that, then this is A is nothing but your gamma R T, right. And from this what you can learn? It is, that means speed of sound is dependent on the gamma. Gamma is what? Specific heat ratio. Will it be dependent on the fluid also? Like suppose if I will take helium, if I take air, what will happen? It will be different, right, and it will be dependent on the temperature also, right. So, let us take this example, like if I take 300 Kelvin for the air, gamma is basically 1.4 and this speed of sound will be 340 meter per second. If I increase the temperature to 100 Kelvin, then the speed of sound is equal to 634. Whereas, for the helium being gamma being different, right, it is basically the 1.66, right, am I right, for helium, right. So, then the speed of sound in helium will be 1019 meter per second, and at 300 Kelvin, at 1000 Kelvin it is 1861 meter per second. So, all these things we are doing to basically talking about Mach number, which is nothing but the ratio of the velocity and speed of sound. So, that is basically Mach number is equal to V divided by A and V root over gamma R T. And depending on this Mach number, we can talk about various regime of flow. One is Mach number when it is less than 0.8, this will be subsonic flow. I mean in this region, here I have plotted speed of sound versus velocity. In this subsonic flow, of course, there will be some incompressible flow as such. Of course, all these things from here to here it is subsonic, because less than 0.8, right. Of course, by definition we call whenever is Mach number less than 1, we call subsonic. It is not true, of course, and when the Mach number is varying from 0.8 to 1.2 in this regime, right, is known as transonic flow. Mach number is equal to 1, it is sonic flow, right. And Mach number varies from 1 point, of course, I could have told like it will be from 1 to 5, sorry, this is 1.2. So, Mach number 1.2 to 5 is supersonic flow, and if Mach number greater than 5 is hypersonic flow. So, what we will do in the next class, that is we will be talking about little bit about various regime of flow again, and then we will be moving at how we can use this term to talk about compressibility and some other things we will take up in the next class. With this I will stop over. If you are having any doubt, we can have a discussion maybe for a couple of minutes. So, then we will stop over here, right.